So in this video I want to talk about the concept of a relation in mathematics. So what we have is the idea that we typically have a quantity or an object or a type of thing that depends on or that can be described in terms of some other quantity or item or thing. So for example, we could talk about a letter grade in a class, and the grade that you earn depends on the numerical score that you earn in a class. So this is a type of relation, the relationship between the numeric score that you earn and the grade that you get. There's a relationship between the cost to fill your car and the number of gallons of gas that you pump. So the cost that you pay depends on the amount of gas that you pump into your tank. The amount that you pay for beer depends on the number of cans of beer that you purchase. The more cans you buy, the more that you pay. So these are three examples where we have one quantity that is depending on or is related to another quantity. And when we have a relationship between two quantities, we can typically put them in an ordered pair notation. So for example, in number one, where we talked about the grade, so the score that you get in a class, comma, the letter grade that goes with it. So for example, if I said 94 as a percent, then that would correspond to an A in a class. And this would be a relationship described as an ordered pair. This is the grade, letter grade, depending on the numeric score that you earn. If gas costs $3 a gallon and you buy 10 gallons of gas, then you're going to spend $30 on that gasoline. So the cost, the amount that you pay, is going to depend on the number of gallons that you pump. So this is a relationship. If I buy 5 cans of beer and it's decent beer, maybe I spend $2 a can, then I'm going to spend $10 for those 5 cans. This is be a relationship between what I spend and the number of cans that I purchased. So in each case we have one thing depending on the other thing. And typically you're going to assign letters to represent things in a relationship. So if we're representing numerical score and letter grade, we might choose letters to represent those as ordered pairs. So here N could represent numerical score, and capital G could represent my grade. So I could come up with a variable, I could represent my ordered pair with a set of variables: gallons of gas, little g, cost to fill my car, C. So as an ordered pair, so that we don't have to write out the objects that are being related. We can use letters to represent them. The cans, little c, the number of cans of beer, and the total cost of the beer that I buy. So these are just ways to describe these ordered pairs without having to spell out everything. We represent the quantities in the relationship using letters. And what's customary in math is that the first variable is going to be what we call the independent variable. I can't underline it down there, it's too low on the page. I'll have to overline it. So the first variable is going to be the independent variable. It's the thing that can vary. And then the second variable in the relationship we're going to call the dependent variable. It depends on the value or quantity associated with the first variable. So the grade that you get is dependent on the score that you earn. The score would be the independent variable. The grade would be the dependent variable that depended on the score. The amount that you spent on gas would be the dependent variable depending on the independent variable, which is the number of gallons of fuel that you pump. That's independent. You could choose to pump 5, you could choose to pump 6, you could choose to pump however many gallons you want to pump up to the capacity of your gas tank. The independent variable in a relationship is also frequently called the input variable. So independent variable or input variable, those are synonyms. And dependent variable is going to frequently be called an output. What is the thing that you get when you choose an appropriate value of the input? So independent variable and input variable are synonyms and in the same sense, dependent variable and output variable are also synonyms. When we have a generic relation in math and we don't have good letter names to give the independent and dependent variables, then we're typically going to use X to represent the input or independent variable, and we'll represent the dependent or output variable with the letter Y. But we'll only do this when we don't have context. Anytime that we have context, we'll want to use good variable names that represent the elements in the relationship. So this is just a little bit more formal definition of a relation. It's just a correspondence between two sets of objects. And in general, what we're going to be doing is relating independent and dependent variable pairs. Here's my numeric score, comma, here's my letter grade that goes with it. So there's different ways to represent in mathematics relationships. You can represent them as ordered pairs, you can represent them in mapping notation, you can do graphical representations sometimes, and sometimes you can represent relations using equations. So this first example is an example of a relation between input and output variables, or independent and dependent variables, using ordered pairs. So here I have a set of 4 ordered pairs. The F is the name of my relation, so my relation is named F, and it has independent variables. So I have an input of -3 corresponds to an output of 2, an input of -3 corresponds to output 0, an input of 0 corresponds to an output of 4, and an input of 1 corresponds to an output of -2. So again, we want to remember when we have it in ordered pair form, it's an input followed by the output that you get if you select that particular input. Or the independent variable comes first and then the dependent variable comes second. And anytime we have a relationship that's been represented using ordered pairs, a small finite set of ordered pairs, we can represent the same relationship using a notation that's called mapping notation. And in mapping notation, what you do is you create a closed object, usually an oval or a square or a circle, some enclosed geometric object. And inside of that geometric object, you list all of the input variables. And in this case, the input -3 is duplicated, so I need only to list it one time. And then I also have an input of 0 and I have an input of 1. So you list all of the independent or input variables in one set, and then you give that set a name. So I'm going to use A. Here's the set A. And the output variables you put in another geometric object. In this case, I'm going to use an oval, and you say, what are the outputs? So in ascending order, my smallest output is a -2. The next smallest output is a 0. The next smallest output is a 2. And the biggest output is a 4. So I've listed all of the outputs that I have, and I'm going to give this set a name as well. This is the set B. And a relation is just a correspondence between two sets. So here I have two sets, a set A and a set B. And in mapping notation, so I started with the ordered pair notation. In mapping notation, what you do is you take the input set and the output set, and then you draw arrows indicating what the inputs map to. So in this case, -3 maps to +2. So I do an arrow pointing from -3 to 2, and it has to be an arrow pointing from the independent to the dependent variable, or an arrow pointing from the input to the associated output. And here I see that -3 also generates an output of 0, so I need to have an arrow going from -3 to 0 as well. 0 gets mapped over to an output of 4, so again I need the arrow to point to the 4, and the 1 gets mapped to the -2. So this is the ordered pair notation being represented in mapping notation instead. It is common to start with something that's been given to you in mapping notation. In this example here, we have we have an independent variable, which is the hike, and then the dependent variable is the distance that that hike is. So the distance depends on the hike. You don't say, hey, it's 10 miles, and then that tells you what hike you're on. You say what the hike is, and the hike determines the length or distance that you'll have to hike if you want to go on that hike. So in this case, my independent variables, my first set is the hike that I go on. I have American Lake, Twin Sisters, Dewey Lake, and Natchez Peak. And then I have distances listed in miles, 3.3 miles, 5.7, 7.1, 7.7 miles. And I've mapped the hike to its distance. Notice the mapping notation requires that I have arrows at the end of those line segments indicating the direction of the mapping. The hike maps to the distance that the hike is. So this is a relationship between hike and distance in mapping notation. And just like we did before, where we took an ordered pair relation and converted it into mapping notation, I could just as easily take this mapping notation and convert it into ordered pair notation. So I could say, hey, I've got this mapping from hikes to distances. Let's give this mapping a name. Let's call it F, for example. And then I could say F is the relation that contains some ordered pairs. What are the ordered pairs that it contains? Well, it has American Lake. And American Lake gets mapped over to 7.7 miles. Close that ordered pair up, so I have the input followed by the output, and then I would go comma, what's the next ordered pair? The next ordered pair is Twin Sisters. And that Twin Sisters maps over to its hike distance, which is 5.7 miles. Close that ordered pair. There's another ordered pair, Dewey Lake, which is off of Chinook Pass, in case you're interested. So Dewey Lake, and Dewey Lake maps to 7.1 miles, comma, and then I have Natchez Peak, which is actually called Natchez Peak Loop, but I didn't include the loop because it would have extended outside of my oval, and it maps to 3.3 miles. Close that ordered pair and close my set notation. So here I've taken something in mapping notation and converted it over into ordered pair notation. So just two different representations of the same relation. Relations can also be represented graphically. So here we have a graphic that represents your year in college versus the GPA that you could be expected to earn if you're in that year of college. So it's the convention in mathematics is typically going to be to put the inputs on a horizontal axis and the outputs on the vertical axis. So here we have a relationship that is given to us graphically, but it could also be represented using, for example, ordered pair notation or mapping notation. So if I wanted to represent this graphical information in mapping notation, I would need two sets. I would need a set that represented year in college. Maybe I represent that with the big Y. And then I know that it's going to have numbers 1, 2, 3, 4, 5. And I would need those inside of a geometric object. The most common error I see in the homework is students not bothering to put it inside of a geometric object and just listing them down. And that would get marked down in a homework assignment. So we create the set, and then and I want to give it a name that makes sense. So year in college, I used Y. I'm not going to use X or little y, but here a capital Y for year makes a lot of sense. And those are going to map over to GPAs. Maybe I'll use big G to represent GPA. And the mapping's going from the year in college to the GPA that you expect to earn. And my GPAs in ascending order are 2.75, 3.00. The next one up is a 3.25. Then the next one up is 3.50. And we have a 3.75. And year one maps to the lowest GPA. So I put the arrow in, pointing from the year to the GPA. In year 2, the GPA goes up to 3.25 on average. In year 3, it goes to 3.5. It drops off in the senior year due to senioritis, so the 4th year in college maps to 3.0, and the 5th year in college maps to the 3.75. So there it is in mapping notation, and we just as easily could have represented it as sets of ordered pairs. So graphical information represents relations. Here I have a graphical representation of ordered pairs. So the relation is the set of ordered pairs, and these ordered pairs have been graphed in the xy plane. So I have an x-axis and I have a y-axis, and again, as ordered pairs, x and y generically represent the input and the output, or the independent variable and the dependent variable. So the x's are going to correspond to the first numbers in each of the ordered pairs, and they should be above the corresponding number on the x-axis. So there's a 1 above the corresponding 1. So those are the inputs, and then the outputs are the y values, or the second number in the ordered pairs, and those should correspond to numbers on the output or the vertical axis. So this 2 corresponds directly to the 2 right here. So this is a finite set of ordered pairs. We could list them directly as a set of ordered pairs, or convert that over into mapping notation if we wanted to. Here's a graphical representation of a mathematical relationship in the xy plane. So we have a horizontal or input axis again, and we have the vertical or output axis again. And the relationship is all ordered pairs that live on this line. And what you want to notice is there's infinitely many ordered pairs living on that line. So we wouldn't want to try to list all of them. If we gave this relation a name, for example, f, we wouldn't want to try to list all of the ordered pairs, because there are infinitely many ordered pairs living on that line. We can also represent relations using equations. So the equation y equals x is a relation between the output variable y and the input variable x. So again, anytime you have x and little y without context, x is the independent variable and y is the dependent variable. So we could represent these as sets of ordered pairs. So I could say, hey, the set of all ordered pairs xy is just equal to input x, and the output is y, but notice that y equals x. So I could actually put x comma x as an ordered pair representation of this graphical and equation representation of a relationship. So here would be an ordered pair representation. Here I have a parabola, y equals x squared. So here I have a graphical representation of the relation. I have an equation representation of this relation. I wouldn't want to try to do mapping notation because there are infinitely many points living on this line. So I wouldn't be able to do a good mapping notation. That wouldn't really be a possibility in this case. I could represent ordered pairs though. I could say, hey, the inputs on the x-axis, and I have outputs based on the vertical axis. And what do they look like? Well, when you input x, the output is y, but the equation tells us what y looks like. Y is just x squared. So when you input x, the output is x squared. Again, it's input followed by output. So final example for relations. Here we have a circle, and a circle describes a relationship between x and y values. So here's a graphical representation of the circle. Here is an equation that actually describes this circle. The circle can be completely described by this equation. So we have an equation and a graphical representation of a relationship between input and output numbers. And I would have a harder time in this. Mapping notation would be out of the question because there are infinitely many points living on the circle. Ordered pair notation would be a little bit difficult. You know that you have ordered pairs xy, but if you take x squared plus y squared equals 9 and you try to solve it for y, what would you need to do? You would have to subtract x squared from both sides, and then you would have to take the square root of both sides, but when we take the square root of both sides, we get a plus or minus. So we get plus or minus the square root of 9 minus x squared. So the ordered pairs could be described, hey, input an appropriate x, and the output's going to look like plus or minus the square root of 9 minus x squared. And this would be a reasonable ordered pair representation of this relationship, with the caveat that you can't put in any x that you want. You can see that x's are really running from -3 right here over to +3, and we would need to take that into account, and that's going to be a topic for a soon to come future video.